Hello everyone, we are Group 18. Our topic is Scenario-Based Collision Generation for Safety Assessment. So, this is a new test. Why do we need to propose a brand new test formulation? Autonomous driving systems require a comprehensive evaluation of their reliability to ensure safety. However, it's very challenging and inefficient to test AVs for autonomous vehicles. AV safety in the real world due to the complexity. For example, it's very hard to do the road testing on the public road. And the next concern is rareness. For example, it's very rare to meet a safety critical scenario on the road. It's a long tail distribution problem. So it's important to intentionally generate safety critical scenarios. The key idea of this problem is to decide a learning-based conditional generation method with a collision scenario dataset. Our input is path trajectories of agents and the topology of the map and the condition. Condition here is like lane change or others for junction crossing, opposite direction, and so on. Output is new trajectory of selected attacker. For example, the scenario here, the red car is the eagle car, the blue car is our selected attacker. So after giving initial scenario and giving a conditional input after my model, so we can generate collision scenario like this. The blue car attack the red car in the future. So the motivation one is a balanced collision scenario. Existing safety critical scenario generation algorithm, for example, king and strife. King is for left figure, strife is for right figure. It commonly shows a concern that they tend to have high frequency for certain collision categories. For example, they both can generate head-on or opposite direction easily, but it's hard to build a lane change or a T-bone collision type. So it won't be desired to validate intelligent vehicles under different collision categories. So let's talk about their collision categories. They focus on the collision angle between two cars, like this. But they didn't consider high-level structure. So we choose 5 scenarios from NHTSA, concluding rear end, junction crossing, like this. Okay. Opposite direction, left turn and another car across the path, they call LTAP. And that's what is lane change. We choose these 5 scenarios for this high frequency of occurrence and economic cost. The next motivation is high time cost in the existing method. For example, in Strife, per scenario generation time is 2 to 3 minutes. For a reason that Strife encode bird-eye view image. The image encoding features cost it too much time to build a collision scenario. So we propose a SOTA topology understanding method. It's called VectorNet. We want to integrate vectorized representation in this task. For example, in the traditional trajectory prediction method, they tend to use rasterized representation on the left figure here. It wastes time to encode much unnecessary information. For example, there's no car and topology in the here, but it still need to encode the pixel here, so it's wasting time. We try to integrate vectorized representation on the right figure here. Encoding topology and vehicle trajectory as vectors, and then we build vectors into polygon to do the graph neural network. We can save time. The next topic is that why we need to collect brand new dataset by ourselves. So we need to talk about the difference between existing work and our new baseline setting. In existing works, they do trajectory prediction first and then they do trajectory editing after that. They do trajectory editing to make the attacker attack the ego card, but they can't generate specific collision scenario. If the collision happens, they think it's okay, but we want to build a specific conditional scenario generation, so we need to do trajectory prediction with our collected collision scenarios. For fairness, we need to do all this setting on our baseline. So we need to discuss why or how we build the dataset by ourselves. We use this tool. It's called Critic Polynomial Planner (QPP). The input is the start point and end point of vehicles property. For example, the position, the angle, the speed, acceleration, and also the time limit. For example, the time limit is 5 seconds, so the scenario will end in 5 seconds. After giving this input, we can get a plane path, like the yellow line. You can see a yellow line here. And we let the attacker to follow this path. We can generate our desired collision scenario. For diversity, we can change many parameters, including angles, like collision angles here, theta, and L, like the length when collision happens. And the time limit, for example, is a 3-second scenario. And last one, goal speed. You can change the goal speed of attacker. So this is the first example of lane change scenario. And the next one, like this, we change theta, goal speed, L. And you can see the scenario is quite different. So we do the automatic collision data generation in Kala. The Kala is a simulator of autonomous vehicle. The first off, we need to collect initial scenarios at different junctions we label on the map. You can see the label on the map. It's town 10 in the Kala, and we also have other towns. To generate a large-scale and diverse scenario, we can change parameters we talk about, like collision, position, goal speed, and time limits. After follow the Critic Polynomial Planner, we can generate our collision scenario. Okay, so after data collection, we have diverse and specific collision scenario, but we finish? No, we expect to test different driving model online instead of collision data collection. For example, is the white car is the attacker and you want to hit the ego card. We can change the ego card to other driving model, for example, like transducer, LBC, plenty, and other driving models. Yeah, so we need to train an attacker to attack the model online. So after we have a dataset is not enough. Let's talk about relative work. The first relative work, social gain. is our first baseline. It's a multi-model and multi-agent trajectory prediction models. It is the first model to present social pooling layer to capture interaction, like interaction of two agents. And for fairness, we need to concate our one-half vector about collision type to add condition into input. So the input will be path trajectory of each agent and condition. The output will be future trajectory of attackers. The next baseline is strive. The first stage is to do multi-agent trajectory prediction to simulate traffic flows, and the next stage is to adversarial optimization. It's editing the attacker's trajectory to hit the ego card. The next one is to solution optimization is to change the driving model to avoid the collision. But we talked about the limitation before for countability. The strive tend to build head-on scenarios mostly, and it's hard to build like T-bone scenarios. Also, for fairness problem, we need to utilize the traffic model in strive and modify it to conditional strive, C strive, by concate the collision one-half vector with the decoder's input feature. So the input will be crop HD map, the image here, and path trajectory of each agent, and also the condition. The output will be future trajectories of the attacker. Also, we need to build a new metric. We call that scenario similarity. Because our goal is to create a specific collision scenario, so it is important to evaluate the scenario is desired or not. For example, we want to build a lane change scenario here, but however, the red car take a U-turn and hit the ego card. Yeah, this collision still happen, but is still lane change collision? No, we know the answer is not. Let's talk about method. The big picture is to input the trajectories of each agent and the condition. For example, it's lane change here. Then we do ego position prediction, and then we do attacker position prediction, and we do trajectory generator. Then we get our output. More detail, we can input initial scenario and scenario type. For example, lane change here. First module, we do ego's collision position, like the bounding spot here. And next, we predict attacker's collision position, like bounding bars here. And then we choose a card to be the attacker, so it's attacker selection prediction. Next, we do the Quantum polynomial planner we talked about before, and after that we can get the generate scenario, an ideal lane change scenario. So the model structure is we take trajectories of each agent and a map into a vectorized representation. Like this, we view this property to be vectors, and then we concate another condition like one-half vector to concate it here. And TC is the scenario time limit. For example, we want a 5-second scenario. So we concat here. And after that, we have the final feature. We do 3 things and cross 3 modules. The first module is to predict the eagle card. The red bounding box is the eagle card's collision position. And the next thing is to predict attacker's bounding box. The green box is our prediction. For example, if we want to build a head-on scenario, the green bounding box here is the best choice. And then we need to select a best vehicle to do the head-on scenario. You can see that the car here and here is not suitable. So after 3 prediction, we can cross a motion planner. We talk about QPP before, and we can get a scenario. So the first module, target predictor, we sampled every 2 meters of each center line in the topology, and we select the best point, which is nearest to the eagle collision position. For example, it's red point here. And then we need to predict another offset to like the red bounding box here and the red point here, the distance. Yes, the green line. You can see that. After that, we can get the eagle bounding box position. The next module, we can predict the offset distance of attacker related to eagle card. For example, the blue card, the attacker is 1 meter on the left of eagle card and 3 meter on the front of eagle cards, and the card front angle distance is near 180 degrees. So after the prediction offset, we can get attacker's collision position, blue bounding box, based on eagle card's prediction. The final thing is to select which card is the best vehicle to do the attack. You can see that there may be many vehicles in the scenario, so we want to choose the most suitable one to be the attacker. For example, to generate opposite direction collision, the oncoming car is the best choice here. So we can get attacker's identity in this module. So thanks for your attention.